This is Lab 4, Oscillations. The goal of this lab was to analyze the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Tracker was used in order to analyze the video and collect different data points. I also used GlowScript in order to create a computational model based on the initial conditions of the experimental model. Both models were then compared using graphs in order to get our results. There were different fundamental principles used. First, we used Newton's second law, which is final velocity equals initial velocity plus net force divided by mass times change in time. So the net force, the two forces acting on the system, was the force of gravity and the force of the spring. So the force of gravity is just negative mg, and the spring force, which it uses Hooke's law, is negative spring constant times s, and L hat is the direction of the force. The energy principle was also used. Our system was the spring, the mass, and then also the earth. So the change in total energy was the change in kinetic energy plus the change in gravitational energy plus the change in spring energy. So the kinetic energy is 1/2 mv squared, spring potential energy is 1/2 ks squared, and the gravitational potential energy was mgh. So now we're going to look at our tracker model. As you can see, the origin of the axis was located at the pivot point of the spring. It was at a slight angle such that I aligned it with the spring originally. The calibration length was 0.7 meters, and we measured each data point at the center of mass for each time frame. This would end up giving us two different graphs which show the x and y position for each data point as it was oscillating. So our calculations and initial conditions. So we were given a mass of 0.402. We found the initial position using tracker. We were able to calculate the initial velocity. The initial velocity was the first moment after it was no longer in contact. We got the spring constant from the lecture video 52, and this is how you were able to calculate it, and got 6.83. Same thing with the relaxed length. We got 0.123 meters. This was also from the lecture video. Neither of these are going to change for our experiment because it's the same spring, and because of that, it's going to be the same spring constant and same relaxed length. So now diving into our code from GlowScript, as you can see, here's the ball's mass, the ball's position, the ball's initial velocity, the gravitational constant. Here's the spring constant we got, the relaxed length of the spring. Here's how to calculate the length of the spring when stretched. Here is how you calculate each of the individual energies. So we had kinetic, gravitational potential, and spring potential energy. And then when looking at a while loop, our total time was 9.402. Then we had to calculate the force of gravity, the force of spring, and you add those to get the net force. Using Newton's second law, we found the ball's velocity and the ball's position. That's going to update each time with the while loop. We use the same equation from before in order to update the length of the spring at each individual point and time. And then here we calculate the change in energy for each kinetic, gravitational, spring potential, and then the total. So now when that code is run, you can see that we get a spring that is oscillating, and the blue ball attached to the spring is the points that are being calculated from our code, and the red ball is the points from our tracker model. So now from that we get our position graph. So we have the x position as well as the y position. You can see that the blue line represents the computational model, the red line represents the tracker model. So you can see there's a slight discrepancy, and that's most likely because of the placement of the center of mass just due to human error, as well as any dissipative forces not being accounted for, such as drag. We were also given this change in energy graph. As you can see, the blue line represents the change in kinetic, the red line represents the change in potential gravitational energy, and the green line represents the change in potential spring energy. We were asked a question for your model system: is the energy principle satisfied? We found that to be true because, as you can see, the orange line, which represents change in total energy, is 0 at all time because the change in kinetic energy and the change in potential energy cancel out. The next question asks us to look at the oscillating periods of both the x and y position. So the X position has an oscillating period of 1.652 seconds, and the Y has an oscillating period of 1.519 seconds. The period for X is larger. This is because in the Y direction there are more forces acting on it, such as gravitational force. As you can see, here there are the results, which are just a summary of everything we've been over. The discrepancies, result of human error, no dissipative force, appearing counterforce such as drag. Then an energy principle was satisfied, and we found that the oscillating periods of X and Y were different.